Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar, Haryana. Today we will be discussing about Fabry-perot Optical Resonator and Optical Gain from the paper Atomic, Molecular and Laser Spectroscopy. We will be able to learn Fabry-perot Optical Resonator and its use in various types of lasers like feedback laser, dye lasers, optical gain and losses in the cavity, optical gain in semiconductor lasers. Fabry-perot Optical Resonator. It is a set of two or more mirrors arranged in such a way that allows the light to propagate in a closed path is called an optical resonator. The optical resonators can be classified in two ways: the standing wave resonator and the traveling wave. The simplest resonator consists of two mirrors and a ring resonator consists of at least three mirrors. A mirror is characterized by its amplitude reflection coefficient R and its transmission coefficient T. A Fabry-perot resonator is a linear optical resonator that consists of two highly reflecting mirrors with small transmission, the transmission through which its resonator exhibits sharp resonances. The incoming light makes multiple round trip within this cavity and suffering partly to each reflection. Different outgoing light rays interfere with each other and giving rise to an interference pattern of multiple waves consisting of concentric rings. The varying transmission function of a resonator is caused by interference between the multiple reflections of light between the two reflecting surfaces. Constructive interference occurs if the transmitted beams are in phase, and this corresponds to a high transmission peak of the resonator. If the transmitted beams are out of phase, destructive interference occurs, and this corresponds to a transmission minimum. Whether the multiply reflected beams are in phase or not depends on the wavelength of the light in vacuum, the angle of the light travels through the resonator theta, the thickness of the resonator L, and the refractive index of the material between the reflecting surfaces. The phase difference between each succeeding reflection is given by phase difference denoted by delta is equal to 2 pi upon lambda 2 NL cos theta. If both surfaces have a reflectance R, the transmittance function of the resonator is given by T is equal to 1 minus R square divided by 1 plus R square minus twice of R cos delta is equal to 1 upon 1 plus QR sin square delta by 2, where quality factor QR is equal to 4R by 1 minus R square. Maximum reflectivity is given by R maximum is equal to 1 minus 1 by 1 plus QR is equal to 4R by 1 plus R square. The wavelength separation between adjacent transmission peaks is called the free spectral range, denoted by FSR of the resonator delta lambda, and is given by delta lambda is equal to lambda naught square upon 2 NL cos theta plus lambda naught, which is approximately lambda naught square upon 2 NL cos theta, where we have deleted lambda naught being small. The FSR is related to the full width half maxima delta lambda of any one transmission band by a quantity known as the fineness. Fineness of the cavity is very important, and it is defined as delta lambda upon delta lambda. The denominator delta is different from the numerator delta, which is equal to pi upon 2AR arc sine of 1 by QR under the root. For the value R greater than 0.5, fineness F is written as pi QR under the root by 2 is equal to pi R 1 by 2 upon 1 minus R. Reflectance of the mirror is C is equal to 1 plus R square by 1 minus R square, which is approximately 4R by 1 minus R square, and C is equal to 1 plus 2f pi whole square. Distributed feedback lasers. In lasers with Fabry-perot type of optical resonators, the feedback is provided by reflection at the end mirrors. These are lasers wherein amplification occurs without resonating mirrors, the necessary feedback being provided by the spatial variation of the refractive index of the amplifying medium. Therefore, these lasers are known as distribution feedback lasers, DFB. Irving Coghlan and Charles Schenck in 1971 invented the distributed feedback laser, and today is the light source for almost all optical communication systems. The principle of these lasers is based on Bragg's law that states that the light waves reflected from different planes in a crystal will be in phase if the following condition is satisfied. 2d sin theta is equal to m lambda. Here theta is the glancing angle. The normally incident light waves will be reflected back at planes if the condition 2dn is equal to m lambda, where d is the separation between the adjacent planes and the refractive index and m is an integer, is satisfied. The energy of the wave propagated in one direction is continuously feedback in the opposite direction by Bragg scattering, thus producing a highly selected feedback. A thin gelatin film which dichromatic added to it deposited on a glass substrate, two ultraviolet beams from a helium-cadmium laser are allowed to interfere on the film. The period of the interference fringes produced on the film is given by 2d sin phi is equal to m lambda. The modulation period is suitably adjusted by changing the angle of incident phi. As dichromate gelatin is a photosensitive medium, the gelatin developed after the exposure contains a examples of DFE laser. The dye rhodamine 6G is added to the gelatin layer, and to the pump this dye, nitrogen laser is used. The wavelength of nitrogen laser is 337 nanometer. The laser output of wavelength 0.63 micrometer is obtained. In a different type of DFB laser, a thin film of gallium arsenide is employed. There is a constructive interface between the gallium arsenide active layer and gallium aluminum arsenide, a layer that acts as a cladding corrugation which provides a periodic structure that produces a feedback. Optical gain. It is understood that the radiation is reflected back and forth between the mirrors of cavity, and there is a loss of intensity as the mirror transmit 1% of incident radiation. There are chances of misaligned mirrors that may cause light to pass out the sides of cavity after multiple reflections. Hence, the losses decrease the intensity after one complete round trip. I is equal to I naught e raised to the power minus 2 gamma watt per meter square. Here gamma is the loss coefficient which is dimensionless, and gain due to stimulated emission increases the intensity after one complete round trip. That is I is equal to I naught e raised to the power 2 alpha t. Again the units are watt per meter square. The intensity after one complete round trip considering the above two phenomena is I is equal to I naught e raised to the power 2 alpha L minus gamma. Now if gamma is greater than alpha L, that is losses exceed the gain, then the standing waves inside the cavity will die out, and to sustain the standing waves inside the cavity, the gain need to be high enough to compensate the losses. Due to gain or amplification, the optical power is increased. Hence, gain is the measure of the ability of a laser medium that can increase the optical power. The intensity gain coefficient can be defined as the increase in photon per unit length of the material, and simply in mathematical notations it can be written as G is equal to 1 by L di upon dl. The gain is also defined as the derivative of logarithm of power as it passes through the amplifying medium. G is equal to ddz of natural log of P is equal to dP upon dz upon P. So in the simple quasi two-level system, the optical gains understood in terms of the difference between the stimulated emission and absorption rates. The gain can be expressed in terms of populations N1 and N2 of lower and excited states. So G is equal to sigma E N2 minus sigma A N1 rho nu C. Here the electromagnetic, after traveling through the medium and writing the energy density in terms of intensity. Accordingly, the rate equation is delta I is equal to dN upon dt h nu. Further, stimulated emission, absorption plus spontaneous emission gives us to write delta I nu is equal to B21 I upon C G nu N2 delta Z H nu minus B21 G2 upon G1 1 upon C G nu N1 delta Z dot H nu plus B21 1 by 2 G nu N2 delta Z difference of phase divided by 4 pi. The first term corresponds to stimulated emission, the second corresponds to absorption, and the third one is added due to spontaneous emission. And the factor half has come in the spontaneous emission term due to polarization of spontaneous photons. The spontaneous contributions can be reduced by selecting narrow frequency, that is by making the solid angle beam very small and also by making L very large. The rate equation then reduces to delta I is equal to h nu upon C B21 N2 minus G2 upon G1 N2 G nu I delta Z. Putting the values of B21 in terms of A21 and lambda is equal to Cn upon nu, delta I upon delta Z becomes equal to di upon dz under the limits A21 upon 8 pi and b pi n square lambda square g nu n2 minus g2 upon g1 n1 into I. Now, because of the population inversion and to obtain the gain, n2 has to be greater than g2 upon g1 into n1. Therefore, Iz is equal to I naught exponential factor g naught nu z. So one can write sigma is equal to A21 lambda square upon 8 pi n square and g nu. Optical gain in semiconductor laser. Optical gain is due to stimulated emission associated with light emission created by recombination of electron-hole pairs. It should be noted that in other laser materials like gas or solid-state laser, the processes associated with optical gain are simple and becomes complex in semiconductor because it involves interacting photons, electrons and holes dealt by many body problems. Optical gain in semiconductor is due to photon induced transitions of electrons from the conduction band to the valence band. Fermi's golden rule characterizes electron-photon interactions in the crystal. So we need to write the transition rate for a single pair of conduction and valence band states. Fermi's golden rule assumes that the electron initially occupies a single state that makes a transition to one of a large number of final states. The difference between the initial and final energy of the electron must be equal to the energy of the photon that induces the transition. Each downward transition generates a new photon, while upward transition absorbs one photon. If the number of downward transition per seconds exceeds the number of upward transition, there will be a net generation of photons and optical gain can be achieved. Optical gain in the material is attained when we inject a carrier density beyond such that the quasi-Fermi levels are separated by energy greater than the band gap. Dye laser. A dye laser is a laser that uses an organic dye as the amplifying medium, wherein the dye is dissolved in a suitable liquid solution like ethyl alcohol, methyl alcohol or acetone or toluene, water. We need to check the solution for a dye. A dye laser is to be used for much wider range of wavelengths spanning 50 to 100 nanometers. That is why these are called tunable lasers. So far dye laser available with us in the visible region from 400 to 700 nanometers. After 700 nanometers, we have a titanium sapphire laser, which is tunable one and is a solid state laser. But this dye laser is a liquid dye laser. The most important dye used so far is rhodamine 6G, can be tuned from 635 nanometer orange red color to 560 nanometer, which is greenish yellow. However, the dye can be replaced by another type of the dye in order to generate other range of wavelengths from the near infrared to near ultraviolet. So dye lasers were discovered by P.P. Sorokin and F.P. Schaffer in 1966. It is important to know about Jablonski diagram that interprets various de-excitation processes possible for an electron that is being pushed to the higher energy level by the assistance of light or heat. The major processes involved are fluorescence, phosphorescence, and internal transfers via solvent relaxation, energy transfer to the foreign molecules. The Jablonski diagram features the energy levels within a molecule where valence electrons could be excited. The diagram is self-explanatory, where it mentions the transitions from ground singlet to higher singlet levels and singlet to triplets and is referred to as intersystem crossing. There are also chances of internal conversion, that means from singlet to singlets on isoenergic states. When we say isoenergic states, that means the states which have almost equal energy, and transition can take place from one state to other state. Dye laser. A dye laser is a laser that uses an organic dye as the amplifying medium, wherein the dye is dissolved in a suitable liquid solution like ethyl alcohol, methyl alcohol, acetone, water or toluene. One need to check the solubility of the dye and select the solvent accordingly. A dye laser is a tunable laser and is to be used for much wider range of wavelength spanning 50 to 100 nanometers. This is why these are called tunable lasers. So far, the only tunable laser is the dye laser in visible region. But where the wavelength of the laser, particularly this dye laser, stops, another solid state tunable laser, titanium sapphire laser is available. So in visible region, only the dye laser, tunable laser is available. The most important dye, rhodamine 6G, can be tuned from 635 nanometer, which is a wavelength color orangish red, to 560 nanometer greenish yellow. However, the dye can be replaced by another dye in order to generate other range of wavelengths from the near infrared to the near ultraviolet. In fact, there is a lot of dyes are available, and the classification of dyes is xanthine class of dyes, coumarines, cyanines and many more. But most tested dye so far is the xanthine and coumarine class of dyes. There are photo bleaching effects associated with the dye. As the light falls on them, they get bleached. There is a healing and cooling property of the dye. When the dye cools, it heals, it regains its original color. Dye lasers were first discovered by Sorokin and Schaffer in 1996. It is important to know about Jablonski diagram that interprets various de-excitation processes possible for an electron that is being pushed to the higher energy level either by the assistance of light or heat. One important thing associated with the use of dye in solution form is that the dye has to be used in millimolar concentration. The higher concentrations of dye are not going to give any lasing effect. The major processes involved are fluorescence, phosphorescence, internal transfers via solvent relaxation, energy transfer to the foreign molecule. The figure is a famous Jablonski diagram, which otherwise is self-explanatory, but one can see the singlets and triplet state of the molecule. There is internal conversion or intersystem crossing. When the transition takes place from one singlet form to the other singlet, then there is internal conversion, and if the transition takes place from singlet to triplet, then it is called inter-system crossing. Although there are internal conversion in triplet excited states, but they can be neglected because before the building up of triplet states, the transition takes place. The Jablonski diagram features the energy levels within a molecule where valence electrons could be excited. It mentions the transitions from ground singlet to higher singlet levels and singlet to triplets, and we had already discussed internal conversion, that is from singlet to singlets on isoenergic states and singlet to triplets as intersystem crossing. The beauty of the dye laser is that the liquid dyes have an extremely high lasing threshold, and flash lamp pumped lasers need a flash with an extremely short duration to deliver the large amounts of energy necessary to bring the dye past threshold before triplet absorption overcomes singlet emission. It is important to keep the triplets away from the participation in the emission of laser. The liquid dyes have very high gain as laser media. The high gain also leads to high losses because of the reflection from the dye cell walls and hence will reduce the amount of energy available to the beam. Chemicals and organic dyes. Rhodamine 6G in chloride form mixed with methanol emits yellow light under the influence of a green laser. Green laser means we will be exciting this dye with ND-YAG laser, second harmonic, 532 nanometers. Some of the laser dyes are rhodamine orange 540 to 680 nanometer, fluorescein green 530 to 560 nanometer, coumarins blue 490 to 620 nanometer, stilbene violet 410 to 480 nanometer. These are the dyes commonly used in dye lasers. These dyes have very broad fluorescence spectra. The dyes absorption and emission tend to center on a certain wavelength and taper off to each side, thereby forming a tunability curve with the absorption center being of a shorter wavelength than the emission center. A wide variety of solvents can be used, although some dyes will dissolve better in some solvents than in others. Some of the solvents used we had already discussed: water, alcohol, hexane, toluene and many others. Flash lamps and several types of lasers like copper vapor laser, diode laser, nitrogen laser, ND-YAG laser, second and third harmonic of ND-YAG laser, ruby laser, argon ion laser, excimer laser and few examples which act as pump source. There can be a generation of ultra-short optical pulses. RL4, B.I. Green and C.V. Schenck has demonstrated in 1981 the generation of ultra-short laser pulses using dye lasers that could produce pulses in picosecond domain, though it has become possible to generate the pulses in femtosecond dye lasers. So, summarizing what we have learned is the concept of Fabry-perot optical resonator that exhibits sharp resonances and application to distributed feedback laser. Optical gain and losses in the cavity, and hence understood that intensity gain coefficient is defined as increase in photon per unit length of the material, and the optical gain in semiconductor laser is also discussed. Dye laser is a tunable source and is of interest due to its tunability found in the visible region. Thank you.